In this module, we'll talk about techniques for site characterization, especially about thermal response tests. The content will be what do we need or want to measure, how to estimate thermal properties needed for the design of ground source heat pump systems, discuss in more detail the in situ thermal response testing, standard procedures, and some special topics. So, estimating thermal properties. Obviously, thermal conductivity, heat capacity, and the vertical temperature profile are very important parameters in the design of a closed-loop ground source heat pump system. In addition to those soil parameters, we also want to know something about the borehole thermal resistance. And the question is how we can estimate all those thermal properties. Now, we start by looking at the thermal ground conductivity and heat capacity. If we have a detailed soil profile, we can calculate a thickness-weighted average. So for every layer that we encounter, we can take a look at what the typical value for the heat capacity or thermal conductivity would be, multiply it by the thickness of this layer, add all those individual parts up and divide it by the total thickness to arrive at an average value for the thermal conductivity or heat capacity. For the thermal conductivity, we can use typical values from reference tables. For the heat capacity, in any case, for porous media, we can also calculate the heat capacity with the formula given, where we have certain factors multiplied by the fraction of organic material, usually something like 3 or 4%, the mineral fraction, and the water content, where the water content is usually about 30 or 25% in sandy deposits. Typical values, where can we find them? For instance, in the norm EN 17522, we find tables of typical values for soil thermal conductivity and heat capacity and density. This 17522 is the European norm for closed loop systems and also a part for water wells. We can see here that for water saturated sand, the indicated thermal conductivity is in the range between 2 and 3. Now, keep in mind that, for instance, in tests in the Netherlands, we've already measured for sand thermal conductivity values up to 3.7. Another parameter that we need to estimate is the ground temperature. Usually the average ground temperature is more or less equal to the average surface temperature, which we can find from climate stations. Shallow parts, so below, let's say, 10 meters, we find the seasonal varying temperature fluctuation. And then at greater depths, we find an increase in temperature, which is caused by the geothermal gradient. The near surface variations we can calculate with this nice equation that we see. For the geothermal gradient, we actually need much more detailed information about temperature increase with depth. You can see a little map here that we've created for the Netherlands, where we have different zones with different thermal gradients. Even in a small country like the Netherlands, this varies between 10 to 15 degrees per kilometer to about 30 to 35 degrees per kilometer. So quite a wide range of thermal gradients. If we also know the thermal conductivity over the soil profile, we can consider it's fairly straightforward to calculate the geothermal energy flux in watts per square meter from the geothermal gradient in Kelvin per meter and the thermal conductivity of that particular vertical profile. Now we have a number of problems with this. For instance, the availability of reference data. How good are our tables of thermal conductivity and heat capacity? A second problem is the availability of drill core data, especially near the location. Even in a country like the Netherlands, where we have a lot of data available, often the closest by drill cores are at 500 meters or 1 kilometer away. Especially when looking for deeper drill logs, 100, 150 meters, 200 meters, the availability of data becomes scarce. And there is an error due to the large potential range of values, like I indicated in the previous slides. For sand, we can find values between, let's say, 1.8 and 3.7 watts per meter Kelvin for thermal conductivity. Moreover, if we only use a desktop study, we do not get any information on drilling conditions, and we also do not get any information on the actual borehole thermal resistance. Using incorrect values for the thermal properties may result in a quite costly over-design or under-design. And therefore, we would like, in certain cases, to be able to carry out an in situ thermal response test.